Welcome to Oddly Real. I'm Nem Stefanovic. We're all familiar with the force of gravity. We can physically feel its effects pulling us down. We can also see objects dropped to hit the floor, sometimes crashing on impact. So gravity is very real. Yet there's something strange about the force of gravity that has led to it being called a fictitious force or a pseudo force. So what does that mean? It turns out gravity may not be like the other fundamental forces in our universe. Additionally, the force of gravity appears to mysteriously reach out over great distances to grip objects with mass. But how is that possible? In this episode, we'll explore this phenomenon, and you might be oddly surprised about the true nature of gravity. Let's start by discussing the concept of a pseudo-force. We take a look at an example of pushing a cup of water across a tabletop. When we are pushing the cup, we accelerate the cup forward. However, this also produces a force within the cup acting in the opposite direction of the acceleration. The water in the cup responds to the force by getting pressed up against the side of the cup. This looks like there's a mysterious force in the cup without any apparent cause, pushing the water against the side of the cup. Of course, we know that the true cause of the mysterious force is due to the acceleration of the cup itself relative to the table. We call forces like this pseudo forces, and they occur due to accelerations of bodies like the cup. In this example, when we stop pushing the cup and friction causes the cup to decelerate, the pseudo force is reversed. This causes the surface of the water to be angled against the opposing side of the cup. When the cup is settled and at rest, the pseudo forces are gone. Pseudo forces also arise in rotating systems. Let's say we have two people. One is on a carousel, Carol, and the other is on the ground, Gord, who watches the carousel turn. Carol sees the objects on the carousel appear stationary relative to her, since she and the objects are all rotating together. Now, Carol wants to walk across the carousel from one end to the other along a straight line through the center. However, as she walks along that straight path, she feels a mysterious force pushing against her to the side. In order to stay on her straight line path, she has to lean in to the side and push, applying a force of her own to counteract the effect as she walks forward. This happens all the way along her path, even at the center of the carousel. This strange force, called the Coriolis Force, appears at a right angle to the velocity of any moving object on the carousel. Gord, who is on the ground, sees things a little differently. Although Carol is indeed following her path through the center of the carousel, Gord sees Carol rotating along with the carousel. From Gord's perspective, Carol is not moving in a straight line at all. Instead, he sees her moving in a curved path. Since Carol moves in a curved path, it means there's a force being applied to cause Carol to curve. In this case, that's the Coriolis force. Another way to think about this situation is to say that there's something weird about the space that Carol is in. The space being the carousel. Of course, we know why it's weird. It's because the space is rotating. That's also the reason why the Coriolis force appears and acts against Carol when she moves. If the carousel wasn't rotating, there wouldn't be a Coriolis force. Hence, the Coriolis force is an example of a pseudo force. On a side note, the Earth is a rotating object. When you look down at the Earth from the North Pole, it is spinning counterclockwise. Objects in the northern hemisphere deflect to the right. Objects will deflect to the left in the southern hemisphere. This produces interesting effects on Earth, such as hurricanes that have counterclockwise rotations in the northern hemisphere and hurricanes with clockwise rotations in the southern hemisphere. These effects are a result of the Coriolis force. Now let's look at an example with the force of gravity. We have two objects separated horizontally at a height high above the surface of the Earth. If we drop the two objects at the same time, they fall towards the Earth, taking paths that look closely parallel to each other. However, they will start to move closer together as they descend. In fact, the two objects will accelerate towards each other due to a well-known effect of gravity called the tidal producing effect. In brief, the tidal producing effect causes an accelerated shortening of horizontal separations and an accelerated lengthening of vertical separations for falling objects. We're seeing the horizontal shortening here between the two dropped objects. Ultimately, the objects will land on the ground slightly closer together than when they were dropped. We can compare this situation to an analogy called the parable of the two travelers. Two travelers are at a planet's equator. They look around and the land appears flat. They are not aware that they're living on a planet which is roughly a sphere. They want to head in a direction north. One of the travelers first separates themselves from the other by traveling a few kilometers east along the equator before sharply turning 90 degrees to face north. As far as both travelers know, they are heading in a parallel direction relative to each other. They both then start walking in a straight line at the same time, traveling at the same pace. But something weird happens. As they travel, they notice they are getting closer to each other. As they continue to travel forward, they start to converge faster and faster. It's as if they were accelerating towards each other. The two travelers are unable to explain how they are converging since they are walking straight along parallel paths. They decide that there must be a mysterious force that is deflecting their paths. Now we know, as outside observers, there isn't anything strange about this at all. The two travelers are converging not because of a mysterious force, but because they are walking on a curved surface, a sphere. So what does this all mean for the force of gravity? In the parable of the travelers, the real reason for the apparent acceleration between the travelers is due to the curved nature of their space. Recall, in our other example, when we dropped two objects from high above the Earth, they accelerated towards each other as they fell due to the tidal producing effects of gravity. However, this effect doesn't need to be explained with a mysterious force of gravity. Instead, the dropped objects start to converge because the curvature of space guides the objects to converge. In other words, there's something different about the space around objects with mass. It's distorted. In fact, a force of gravity is not necessary even to describe a falling object. We know that if we are on Earth and we hold an object, it falls when we let it go. It appears that there's a weird force pulling the object down to the ground. However, this isn't exactly the right way to look at it. In fact, it's not the object's behavior that we should be worrying about. It's our own. A better perspective is to try to understand why a force has to be applied to the object to keep it from falling. The object wants to do the most natural thing possible, remain at rest, or if moving, stay moving at that same velocity. However, it's us on Earth that are being held up unnaturally against the surface, and it's us from this held position that we're looking at the falling object. Instead, let's get rid of the ground so that we're falling with the object in hand. Now we don't experience any forces at all. We feel weightless. So what happens when we release the object from our hand? The object stays put, falling with us, exactly in sync with us as we fall. There is no force of gravity anymore, for us or the object. Additionally, if we think of the curvature of space as being the reason that mass is guided along its direction of motion, like when an object falls, then there's no reason to think of the force of gravity as an action at a distance. Masses in a region of space move based on the local curvature of that space. They are not being told to move from a long distance away at all. A large object like a planet will distort the space around it, and masses that pass by will be influenced by the curvature of the space in their immediate area. You might wonder, if a large object like a planet moves through space, like in an orbit, how quickly will the curvature of space change? It turns out it takes time to curve space. The changes propagate at the speed of light. It is not an instantaneous change. We've seen that space is actually not flat around massive bodies, but has a curved geometry. In reality, our universe actually exists not just in 3 dimensions of space, but in 4 dimensions. 3 of those dimensions are space, and 1 dimension is time, and together they are called space-time. It turns out that mass curves space-time as a whole. When space-time curves, both space and time experience distortions. If we take the example of our sun, the time warpage at the surface causes time to flow more slowly by 2 parts in a million, or 64 seconds per year, than if you were far away from the sun. It's even more pronounced at the sun's center, where time is running slower by about 1 part in 100,000, or 5 minutes in a year. This doesn't sound like much, but the effects can be truly dramatic around much more massive objects like black holes. Ultimately, it turns out that space-time tells mass how to move, while mass tells space-time how to curve. We've only scratched the surface with our discussion of pseudo forces, gravity, and space-time curvature. However, I hope you found it interesting. Remember, oddly real, really interesting.